introduction. My name is Sven and I want to talk about my research topic, miniature optical fiber, which was able to measure the temperature and the pressure at the same time, and it's used for a medical application. I structured my presentation in 6 chapters. In the first one, I want to talk why it's important to measure pressure and temperature in the medicine and why to use optical fiber for this. Then I want to explain the theory behind the sensor and the idea what we have. After this, I want to show some experimental approach, and at the end I want to show some analysis and results. Yeah, let's start with the introduction. In the medicine, it's important to measure temperature and pressure, but many times it's not so easy to reach some areas. So it is sometimes very difficult, and it would be very nice to have a small sensor to reach difficult areas. Also, it would be nice to have a sensor which measures 2 things at the one time, because it's not so comfortable for a patient to have many sensors in the body. And of course, the sensor shouldn't affect the normal behavior. So because of this, an optical sensor would be a very good idea. It's a very good idea to use it in a medical area. So an optical fiber is made of quartz glass. It's biocompatible, and because you can transmit the signal on a long distance, you can even measure it on another room, and it is not very expensive, so you can fabricate very cheap. Yeah, let's talk about the theory. I want to talk about theory behind the sensors. These are 2 things: the Fabry Perot Interferometer, the FPI, and the Fibre Bragg Grating, the FBG. So let's start with the Fabry Perot Interferometer. What is an FPI? If you have 2 glass plates like here, an incident light beam is reflected and it's also transmitted, and the transmitted light beam is reflected as well and transmitted through the first glass plate, and this both light beams interact with each other, so they interfere. And the good thing about this is that the interference can be calculated, and it depends on the gap length. So if you change the gap length, the best fit wavelength is changing as well. And if you have a look to the wavelength, you can see that the peak position was moving. So you can calculate actually the gap length between both glass plates. Yeah, the second one is the Fibre Bragg Grating. The Fibre Bragg Grating is a changing of the refractive index in the core, and it's periodical. And if you send broadband light through the fiber, you will see that the Bragg wavelength will be transmitted, reflected, and the other wavelengths are transmitted through the fiber. Yeah, let's talk about the idea behind the sensor. The sensor is made of quartz glass. So in this case, it is surrounded. The single mode is surrounded by a capillary, and at the end there's a diaphragm. This diaphragm and the single mode, these are actually the Fabry Perot Interferometer. So if the cavity is sealed and the pressure inside the cavity is constant, like at the outside, then everything stays like it is. But if the pressure is changing, the cavity is bending. This is like we saw it before in the FPI. The gap length is changing, and because of this, the wavelength is changing as well. But the big problem is that the cavity is made of quartz glass and is very temperature dependent. So if the temperature is changing, there is a drift as well. But because there's a drift and you want to measure the pressure. So the cavity is changing with the pressure and the cavity is changing with the temperature. A temperature drift can misunderstand as a pressure drift. So the idea is to put an FPG very near to the capillary, so in the near of the cavity, and we calculate with the FPG the temperature as well, and with a compensation matrix we are able to calculate the temperature out of the cavity. Yeah, the second idea was to use an interpolation because we want to use it in a medicine area. It is very important, or it's very nice to have a handy device. So we used a small interrogator, but the small and inexpensive interrogator has small resolution. So we used an interpolation to get a higher resolution at the end. Yeah, let's talk about the approach. On the right side, you can actually see one of the probes. This is the single mode in the capillary, and at the tip you can see the diaphragm. It's very, very thin, and the probe by itself has a diameter of 200 micrometers, so it is very small. Yeah, there are several steps to do. The single mode is surrounded by a capillary. They are spliced together, and at the end there is the single mode, the multimode. The multimode is spliced to the capillary. It's cleaved and polished down, and in the and we used an HF asset to get an even smaller diaphragm. Yeah. During the whole process, we have to measure many properties. So we're using the interpolation all the time. During each step, everything is saved in the configuration file. After the sensor is prepared, we measured it while during some tests like a pressure or stability test, and everything is saved in a configuration file which is used later while during the measuring. So the signal, if you have the instrumentation, you have your broadband source, you have your interrogator and your probe, and the signal from the interrogator is compensate. And after this, the signal is split into the FPG part and the FPI part. The FPG part measures the temperature, and the FPI part measures the gap length, and with this the pressure. And but there's still the problem with the temperature, and at the end we calculate with the compensation matrix the real length or pressure. Yeah, here's a picture of our equipment. It's described in the paper more in detail. I only wanted to show it. Yeah, let's talk about some results. We tested the sensor in a pressure chamber. So we used a reference sensor, an MPX sensor, and you can see that the sensor fits the reference sensor pretty well. We even tested it in a fluid system, so we got a resolution better than 2 millimeter per mercury, and this is enough for a medical application. And we even wanted to know the stability. It is very important to have a stable sensor. So if it's used in the medical area, you want to be sure that after 20 or 30 minutes, that if you get, like in the case of the OFPS sensor, if you get a rise of the signal, it is not the sensor which is changed, that is really the patient, where the condition of the patient which is changed. So the stability is very important. And as you can see, our sensor was stable even after 40 minutes. There was a noise of 1 millimeter per mercury, but the OFPS, this is a sensor you actually really can buy, has a drift of several millimeter per mercury over 40 minutes. Yeah, we even tested the sensor in a cardiovascular simulator. So this is this device. there's actually a plastic heart in the middle which is really pumping, and we measured the signal with the opsons as well, and as you can see, our sensor fits the opsons quite good. Yeah, I want to come to the conclusion. You saw that the sensor fits several requirements, like it's very small and it's biocompatible. Even the resolution is very good, and it's pretty stable. So I think it can be used in the medical area, but there's still some future improvement. So we want to pack everything together so that it's very handy in a medicine area. We want to, or we will test it next year in a real patient under real condition, and yeah, of course, we have to aggregate it for medical usage. Yeah, I want to thank the SFI for financial support, and the MSSI and the CES of Limerick for some facilities. Thank you for your attention, and if you have any question, I would like to answer them.